Okay, welcome back homeowners and future electricians. This is part 2 of how a ground fault circuit interrupter works. Remember, it can be a circuit breaker or it can be a ground fault receptacle. All right, new term, current transformer or a CT. Remember, flow of electricity, AC current creates heat and magnetism. A current transformer senses the magnetism and then it can be displayed on a digital or analog display. I have my Klein tools. This here is a clamp-on ammeter. There's a metal core in here that senses the electricity and puts it out on a display. Very useful for electricians to use if you want to be an electrician. Okay, I'm not telling you have to use Klein tools. There's other brands out there. Now, when I was teaching at night, second and third year apprentices for the federal apprenticeship program, I rigged up this little board and I bought some current transformers, okay? They come with these little packs here. I'm going to plug this into a ground fault receptacle. Okay, right now there was no current flowing, okay? And I made up a little circuit here, parallel circuit, which I explained earlier. And what I did is I hooked up CT number 1 over here so that it's measuring the total current. CT number 2, I showed you at the beginning, there's a photo of the power resistors on the back here. Okay, welcome back homeowners and future electricians. This is part 2 of how the one big one represents a hair dryer that pulls a lot of current, about 11 to 12 amps, okay? And also I have CT number 3 is hooked up to a simulated curling iron. And what will happen here now is I'm going to turn on the hair dryer. And as you can see, the circuit is approximately the same. These are not very expensive current transformers, so there may be some discrepancy between the two. So right now the total current here equals the current going through the hair dryer, okay? Now when I turn on the curling iron, as you can see, the curling iron is pulling much less amperage than the hair dryer, and together they equal approximately the total current here. All right, now if I turn off the hair dryer, you can see now the total current equals approximately what we have flowing just through the curling iron, okay? Okay, now I took my current transformer number 1 over here and I put it on our neutral or ungrounded conductor. Now, when I turn on the hair dryer starts to pull amperage. Now you can see the current that was going out here is returning on our neutral conductor. Now I add in the curling iron. You can say it's the same thing. Both of these approximately equal to both of them on. I turn off the hair dryer and now the current of the curling iron only is flowing back on the neutral. This is the way an electrical circuit is supposed to operate. There's no faults involved here right now, okay? Okay, welcome back. Now, before, the current on the hot or ungrounded equals the current on the neutral or grounded. What I did is I purposely took the neutral connection of the curling iron, okay, and I connected to our grounding conductor, our green or our bare. So now we have a ground fault. Right now I have this plugged into a non-ground fault receptacle, okay? And this is only for demonstration purposes. I'm going to turn on my hair dryer. As you can see, the current that's flowing out to the hair dryer equals okay, the current coming back on the neutral or ungrounded or grounded terminal rather, because I have my current transformer over here. I'm going to turn the hair dryer back off. Now I turn on my curling iron. Now, current transformer number 3 shows the current going out to the hair dryer. But as you can see, current transformer number 1, which is the neutral, has no current flowing on it. That's because the current is flowing to ground, okay? That is a ground fault. Now I'm going to plug my tester, my test kit here, into a ground fault protected receptacle. So now our circuit here is ground fault protected. We turn our hair dryer on. Okay, your daughter, mother, wife, whoever goes to turn on the curling iron. Now the ground fault receptacle sensed that ground fault, that there was an imbalance between the hot and the neutral, and the ground fault receptacle immediately tripped off. Okay, to give you a little visual of what a improper ground fault protection can look like, I just want to advise you, no Barbies were harmed during this production. So anyway, this is someone you love. They're using their hair dryer, okay? Everything is fine. When they go to turn on their curling iron, okay, there is a ground fault. As you can see, the current from the curling iron is not flowing through the neutral. It's flowing on a ground fault, but since there's no ground fault protection, Barbie's hair is going to stick up. Now I have this plugged into a ground fault protected receptacle. This will show you the importance of having ground fault receptacles in your bathrooms, kitchen, outdoors, etc. So we turn on the hair dryer, and the current, all right, that is flowing through the neutral equals the current that's flowing on the hot conductor. And now as soon as I turn, or as soon as Barbie, and no Barbies were harmed, don't forget that, as soon as we turn this on, the ground fault receptacle senses the ground fault, trips off, and Barbie is safe. Thank you.